So, new set of guided notes. We're going to be talking about probably the most important topic in statistics. I think if you ask any statistician or someone who does like accounting, things like that, or anyone who deals with statistics, they will tell you that the most important topic in statistics is this thing called the central limit theorem. Okay. Now, I find this theorem very, very confusing to kind of understand. It's kind of a hurdle to get through. But once you kind of understand the background behind it, there's only one really specific question you can be asked about the central limit theorem. Okay, so we'll get there. We're going to do a small example in the beginning, and don't really worry if it kind of confuses you or like throws you off at the beginning. We're not going to be doing all the work that we do for this one example at the end. We're just going to answer a very specific type of question. Okay, but before we get to that example, I want to give you some symbols that we're going to be using throughout this section and kind of like the next sections that we're going to be going over. And it kind of depends if this number talks about like a population or a sample. And it's going to be very obvious that you're working with a population or a sample. Okay, so this will be very important for your quiz on Friday. I'm going to ask you for 4 different symbols. Okay, first one is the population mean and the population standard deviation. Okay, and these symbols are the symbols that we've already learned about the mean. Does anyone remember the symbol for the mean that we've used before? Oh, sorry, I thought you said mean. I was like, yes. Yes, it's mu, right? The mu symbol, it kind of looks like this, right? It's a U with a little line on the bottom. What about standard deviation? I see Shelly making it. It's the circle with the line on top, lowercase sigma. I think Sanjun said it looked like a cherry. I kind of like that. Okay. So I introduced these symbols as just the mean and the standard deviation, but it's not just the mean and just the standard deviation. It's technically only used for the population mean and the population standard deviation. So whenever these numbers are describing like the population or the total amount of things that we're actually interested in, we're going to use these symbols. Okay. Let me introduce to you 2 more symbols for samples. Okay, so whenever we're talking about a sample, like a small group of people that we take out of the whole population, we're going to talk about the sample mean being X bar. Okay, and this one's really easy. Sample standard deviation is S. So 4 different symbols that are going to be very important for our quiz. Okay. And we're going to be using these a lot. So if you ever get confused, just go back to the tape chart and you can kind of refresh your memory on what these symbols mean. Okay. We're going to go back to like the first week of class when we talked about sampling. We talked about samples and we did a lot of work with like the different types of samples we can have and how we can create a sample that best represents the population. And I think when I first introduced samples, I drew a rectangular prism, right? Let me try to do my best shot at doing this. Here we go. Oh gosh, that's not good. That's fine. Okay, so pretend I drew a nice rectangular prism there. And I talked about a sample as being something called a cross section, right? Or a slice of a cake, where I kind of took a little piece out of the rectangle or the rectangular prism. And I only considered that slice, right? I called this a cross section. And I kind of chose a random cross section out of this to be my sample, right? So our population is our prism. The cross section is our sample. Okay. Now, I like this idea of the prism because the cross section was like kind of a good representation of any sample that can come out of this population. Any prism, or sorry, any cross section that I took out of this prism would be a representative sample because all the samples would look alike, right? Now, did it matter that I took a sample from the middle? Could I have taken it a little bit closer to the front? Yeah, right. It didn't matter that I took that specific cross section. I could have even sampled, I don't know, like the very front, right? Or the very back. Try my drawing skills out here. Okay. So it didn't really matter where I took my sample out from, because there's many different samples within a population. Okay, so in a population, there are going to be multiple different samples that you can take. To drive my point a little bit further, let's just pretend, I don't know, let's do an example here. Let's just say my population is like this entire class, right? And maybe I was interested in like how tall everyone was, right? This class is heights. Okay. There's many different samples I could take out of here, right? So some examples, maybe I wanted to take a sample of size 2, okay? Well, one example might be, I don't know, Shalea and I don't know, Anastasia, right? That would be a sample of size 2, right? Or I could take, I don't know, I could take TJ and Emma, right? So I can create different samples of different sizes out of my population. Oh my gosh, out of my population, and all of them would be a little bit different. Okay, and for each of these, I could find the sample mean of Shalea and Anastasia, the sample mean of TJ and Emma. Right? I could take the mean of their 2 heights. So in a population, we have multiple different types of samples that we can take out. And there's going to be a sample mean for every different type of sample we take out, right? Shalea and Anastasia are going to have a different sample mean than TJ. So the main topic behind this important theorem, the central limit theorem, is this thing called the distribution of the sample means. Let's think about that word here. Well, we kind of talked about what sample means are. We're pretty strong on that topic. Does anyone remember what the distribution means? TJ?
Is it like the spread of data?
Yeah, like how they're spread out, right? I think when we talked about distributions, we like drew lines on top of histograms and we try to figure out like what the shape of the histogram was, right? So the distribution is kind of like the shape or the spread of whatever we're looking at, right? So we're looking at the shape or the spread of all the different means that we have. Okay. In particular, we're going to be talking about the mean of the sample means. Okay. I know that's kind of crazy to wrap your head around now, but I think when we do an example, we'll kind of clear things up. Okay. So big idea. Samples are all going to be really different out of a population. They're all going to have different means. We're going to see if there's going to be some sort of pattern in the sample means of our population. Okay. Let's go to our next page. So we've got an example. I like this example because I think it makes you kind of think about what type of samples we can have, what type of samples can we not have. Okay, and let's just say I have a group of 6 people and I numbered them from 1 to 6. So there's person 1, person 2, all the way to person 6. I want to take a sample of 2 people, just like I did in my last season. Okay. In order to do that, I decided to roll a dice 2 times. Okay. So like if I rolled a 2 and then a 5, then I'd pick person 2 and 5. A bad example would be rolling a 6 and then a 6. That can't happen because I want a sample of 2 people. So I would have to just roll again until I get 2 different numbers. Okay. First thing I want to talk about is we're going to deal with the population first, and then we're going to talk about the samples. Population mean. I guess to do that, I would have to do the whole sampling distribution, create that chart of the possible X values and their probabilities, kind of like how we did right before the break. Okay. So let me make a small chart, and I will never ask you to do this on your own. We're kind of just setting ourselves up, okay? I guess the possible values I could have is person 1, person 2, person 3, person 4, person 5, and person 6, right? Those are all our possible things that can happen, okay? And the person is chosen with a die roll, right? So what's the probability of like choosing person 1, for example? 1/6, good. And choosing person 2 is also 1/6, right? And don't worry about how I'm getting these. I'm not going to ask you to do this on the test and kind of just setting ourselves up here. Okay, so the population mean, kind of just looking at the population, everything has the same probability, right? Person 1 all the way through person 6 has the same possibility of being chosen, okay? Now you can calculate this on your own, but I'm just gonna kind of skip a step here and show you that the population mean is 3.5. Okay, we would find this by multiplying across the columns and adding them up, but don't worry about it now. And the population standard deviation, I'm gonna give it to you as 1.708. Okay, so just keep this in mind as we go through this activity that our population mean was 3.5, population standard deviation was about 1.7. Okay, here's the big question. How many different samples are possible in this situation? Any ideas? Yeah, so this is a tricky question. This question kind of makes you think about how many different samples we can have. I think the best idea is maybe just try to write out all the possible things that can happen. Okay, so I'm gonna give you like 2 minutes. Try to work together, try to figure out what are the samples that can happen. Remember, they have 2 things in them, 2 numbers. And I want you to figure out how many different samples there are and list them out. Okay, I think I confused you guys enough. Let's come back. Okay, I'm not gonna ask you to do this on a test or anything, so don't freak out yet. I kind of just wanted you to think about what type of samples we can have here. So let's try to put this together here. Person number 6 and person number 5 as a sample, and 5 and 6. Are these 2 different samples? No, right? Because oh my God, yeah, no, because I'm still in spring break road, I'm sorry. Let's just say if we named person number 6, like Bobby, and 5 was Sally. If we just reordered them, Sally and Bobby in a different order would be the same sample. Okay, so 5 and 6 and 6 and 5 are 2 of the same sample here. Okay, they mean the same thing, so I don't need to count these 2 twice, okay? Also, 6 and 6 doesn't make sense because that's not a sample of size 2, that's a sample of size 1, right? So these guys can't be a part of it either, okay? Now, as I was walking around, I saw some good ways of organizing these values. This is what I would do here, okay? Let me just start with 6 and 5. 6 and 5 is a good sample of 2, right? Let me try to go through this a little bit more systematically. I guess we could have 6 and 4, right? 6 and 3, 6 and 2, and 6 and 1, right? These are all different samples of size 2, okay? Let's just say I wanted to start with a 5. Would 5 and 6 be a different sample than what I've had here? No, right, because it's the same as 6 and 5. So I'm not gonna write 5 and 6. Am I gonna write 5, 5? No, right? So I guess I have to start with 5, 4 this time. 5, 4, 5, 3, 5, 2, 5, 1. Okay. Going down to 3. Well, can't write 3, 4 because, oh, no, I can write that. Sorry, I can't write 3, 5 because I already wrote that down. I can't write 3, 3. So I guess I'm left with writing, oh my goodness, I can't. Amy is still in spring break mode. I am very sorry. I skipped down to 3 and I forgot 4. Okay, I can't write 4, 5, and I can't write 4, 4. So I'm left with writing 3. There we go. Oh my goodness, I need more sleep. And 3, 2, 3, 1, and 2 and 1. Once I get down to 1, the only sample I can write is 1, 1, which wouldn't work. So I'm only left with these as my samples. I have written down every single possible sample. Okay. Any questions on how I got here? Okay. Oh yeah.
So when I do it, I do the same thing.
Yeah,
Is that the same idea?
it's the same thing, right? Because I guess what you're doing is you're doing things but in a different order, right? So we've
Different
got
diagonal.
1, 2, yeah, 1, 3, 1, 4. It'd be like this one flipped across the diagonal. Yeah. All right. Okay, so I'm not gonna ask you to do this on a test or quiz. Don't worry about it yet. We're kind of building ourselves up to our final answer here. Okay. So let's flip our page. And I know you're not gonna like me for doing this, but I'm just gonna rewrite all our samples on this chart. I'm gonna write them very small because we're gonna be doing something with each of these. 3 and 1 and 2 and 1. Okay, so I just wrote them on this chart. I left some of them blank just because they don't really fit in this chart, but it's a good way to organize each of our different samples. I guess in total we have 15 samples, right? Now, the whole central limit theorem talks about the distribution of the sample means, right? So maybe, since I have all my samples up here, maybe I should just find the sample mean for each of the samples, right? I meant to write that in a darker purple. Okay, so just starting with the first box, how would I find the sample mean of 6 and 5? I think I heard it. Good, add them together, divide by 2. There's 2 numbers, add them together. 6 plus 5 over 2 is 5.5. Okay. Okay, can do it with 6 and 4. Add them together, divide by 2. How about this? Take some time, add these together, divide by 2, find the sample means. It's kind of boring, but we'll get there. How about this? This side of the class from TJ over, start on the top row. This side of the class and over, start on the bottom row and go up. So top row go down, bottom row go up. Meetings all day. All right. So anyone who did the top row want to read me out the top row?
5.5.
Yeah.
5,
Mm-hmm.
4.5.
Mm-hmm.
4.
Good. Anyone who did the second row? All right, I already have these written down. So I got 4.5, 4, 3.5, and 3. I've got 3.5, 3, and 2.5. We've got a 2.5 and a 2, and then a 1.5. Okay. So basically what we did is we found every single possible sample that we could make out of this situation, right? And then what we did is we went through each sample and took the sample mean and found a number, right? Now, let's find the distribution of the sample means. Okay. Let's scroll down here. I've made a little graph here. And I know I've talked you through making histograms and bar graphs. We're going to make kind of like a makeshift bar graph here, even though we're dealing with quantitative data. Okay, what I'm going to do is I'm going to count every single time I see a 1.5. I guess that's 1, right? There's only 1.5 on this chart. So if 2 boxes on the y-axis equals 1, okay, 1.5 would go up to about here, right? So I guess if I were to make a bar graph, there's only 1, 1.5. Okay. Looking over at twos, looks like there's only 1 2. So I guess we can do that here. Okay. How many 2.5s do you guys see? Oh, yeah, 2, right? I think I wrote one of these wrong. 2 2.5s. All right. I guess there's 2 3s. Everyone agree with that? All right. Okay, we got 2 3s. How many 3.5s do you guys see? 3, good. We got 3 3.5s, all right. Nice. All right, I'll kind of give the rest to you. There's 2 4s. There's 2 4.5s. And then there's 1 5, and there's 1 5.5. So we went through our sample means, we created a bar graph, which kind of helps us see the distribution. What do you think best describes the shape of this bar graph? Symmetrical, good. Is there a different distribution that you think, or is there a specific name for distribution you can use to describe this? The bell curve, right? If I took a, let me try to make this a little bit easier to see here. Let's just say I took like a highlighter and try to draw a line that best represented this data. It would kind of look like the bell curve or the normal curve, right? So this definitely looks like the normal curve or the bell curve. Okay. Huh, that's weird. The distribution of the population wasn't a bell curve, but when we created the sample means, our distribution ended up being normal, right? That's kind of strange. Let's do something else. Let's find. We don't just have to make a graph. We can actually find the mean of the sample means. I just wrote something weird. I wrote the mean of the sample means. Okay, let's break this down. The sample means are all these numbers up here, right? So if I were to find the mean of the means, what would I do to these numbers? Yeah, add them up and divide by 15, right? There's 15 numbers. Okay, I'm not gonna actually write all this out, but I would take 5.5, 4.5, all the way up to 1.5 and divide by 15, and that gives me 3.5. The mean of the sample means is 3.5. Okay. Now we don't just have to find the mean, we can also find the standard deviation of those numbers, right? The standard deviation of the sample means. And I'm not going to make you go through this calculation, but if I took all those numbers up top in that chart and found the standard deviation of those means, I would get 1.2077. Okay. Now, I want you to go back to our population mean and our population standard deviation. What do you notice about these two numbers when you compare them to our population numbers? The means are the same, right? Well, that's kind of freaky, right? The population mean was equal to the mean of the sample means, not the standard deviation, right?
How would you get the standard deviation again?
Oh, so the standard deviation is kind of a crazy calculation. I think you have to square all the values. Oh my goodness, put me on spot here. No. Find the mean, subtract the mean from all the values, square them, add them up, and divide by how many there are. I can show you an example later after class if you want me to. Okay, but I wouldn't make you find the standard deviation of 15 numbers. I think that'd be crazy. Yes. Okay. But I found this on a calculator. Okay. So comparing our mean of the sample means to the population mean, we got the same number. Comparing the standard deviation of the sample means to our population standard deviation, we got a different number. Okay. And then our shape of our graph turned from something that had the same probability for every single value to something that looked like the normal distribution. Okay. Now I'm actually going to say there is a relationship between the standard deviation of the sample means and the population standard deviation. It actually turns out to be the population standard deviation over the square root of our sample size, which was 2. That's kind of how it ended up here. Now I'm going to simplify this a little bit for you. You don't have to go through this whole example ever again, but I think it does show that when we start out with a population. Oh,
Sorry, what is the symbol on the bottom?
Oh, yeah. Let me label these. Sorry about that. So this one's the population standard deviation, right? And N here stands for the sample size, which ended up being 2. Sorry about that. Yeah, I think this example shows how we go from something that doesn't necessarily have to be normal, but it ended up being normal when we found the sample means. And the distribution of the sample means had the same mean and a slightly different standard deviation found by this weird calculation here. Okay. If things aren't making too much sense, don't worry. We're working our way to this crazy theorem here called the central limit theorem. Let's read this. This is a very important theorem. There's a lot of things going on here. But I think once we get through a few examples of using this and we do a little bit more practice, I think we'll get the hang of it. Okay. So this says, if either the sample size n is bigger than 30, or if the population is approximately normal, then something happens, okay? So for this theorem to even work or even apply to something, the sample size n has to be bigger than 30, or the population has to be approximately normal. So either one of two things has to be true. Okay? The thing that's true, if one of these things is true, is that the distribution of the sample means, the graph that we just drew, will be normal. We'll have that bell curve, and the mean of the sample means will be equal to the population mean. Okay. Now I know there's a funky symbol here. Don't really worry about the funky symbol. This just means the mean of the sample means. Okay, that's all that symbol means here. Okay, I'm never going to require you to know what that symbol means, but I do want you to know that it's equal to the population. Okay. Furthermore, the standard deviation of the sample means, will equal our population standard deviation over our sample size n. Okay. So things I don't want you to worry about. I don't want you to worry about the symbols here, the mu sub x bar or the sigma sub x bar. All you have to know is that stands for the mean of the sample means and the standard deviation of the sample means. But I do want you to memorize these two formulas here. Population mean and sigma over the square root. Okay. I know this sounds a little crazy, but I think once we get through a few examples, it will make a lot more sense. Okay, let's do an example. This is the one type of question that I'm going to ask you about the central limit theorem. Okay, let's kind of set this up. We have a sample of size 45. Okay, so when I do these questions, I like to write down everything the question gives me. So I'm going to write down that n is 45. N stands for the sample size, right? Okay. So this sample of size 45 will be drawn from a population with mean mu equals 15. I'm gonna write that down. And the standard deviation is 3.5. Okay, this question is going to ask us, is the distribution of the sample mean so? Okay, whenever you see this question, we're talking about the central limit. Okay. This question is asking us is if either the sample size is bigger than 30 or if the population is normally distributed. Is that true? Is either one of those true? Which one? Yes, right? So we know 45 is the sample size, is bigger than 30. So yes, the sample means are normal. Okay, so if either the sample size is bigger than 30, or if the population is approximately normal, then yes, the sample means are normal. Okay, so first part of the question is done. Why or why not? I wrote that down. If so, we're going to find the mean of the sample means and the standard deviation of the sample means. Okay, let's do the first one. The mean of the sample means. Okay, sometimes I'll write X bar for the sample means, okay? Or I can just write sample means. What is the mean of the sample means in this question? Got it. 15, right? Because, oh, the equation kind of tells us. The mean of the sample means is equal to the population mean. So this is just 15, pretty easy, right? What's the standard deviation of the sample means? How would I set that up? How would I find this value? Close. Good, good. Nice job, guys. Okay. So 3.5 over the square root of 40. When I calculate this, it might be tempting to write this in your calculator. I find that I kind of don't find the right answer when I do this. My best bet for you is to first do the square root of 45 in your calculator. Okay, so go in your calculator, figure out what the square root of 45 is. I actually didn't follow my own directions when I did these notes, so I'm going to do it myself here. The square root of 45 ended up being 6.71. Okay, and I'm going to write that still in the denominator. And then I'm going to go ahead and do the division. 3.5 divided by 6.71. And that gives me 0.52. Okay. So there were kind of three parts to this question. The first one was to explain why the sample means was normal. Second, finding the mean, and third, doing that calculation to find the standard deviation. Okay. Any questions on example 1? Okay. I'm going to walk you through example 2 and example 3. We might not have enough time to do some on your own, but we'll start with that next class. Okay. Example 2, we have a sample of size 8. Well, n is 8, right? And this is drawn from a normal population with mean -60 and standard deviation 5. Okay. Who thinks the distribution of sample means is normal here? Why do you think so? Good, good. So here, well, 8 isn't bigger than 30, right? But we still have that other option that can be true. Since the question says it's drawn from a normal population, okay? Population is normal. We can still say that yes, the sample means are normal. So yes, the sample means are normal. Okay. Okay. What's the mean of the sample means here? Good, -60. Okay, I'm writing X bar just to write sample means a little bit shorter, okay? And how would I set up the standard deviation of the sample means here?
5/8.
Awesome, 5 over the square root of 8. Remember, when you're calculating this, do the square root of 8 first in your calculator and write it down so you don't make a mistake. I didn't do that, but I'm getting 2.83 on the bottom, okay? Then I'm gonna go and divide 5 divided by 2.83 to get 1.78. Okay. Any questions on how I got these two values? All right, let's do the last one. Here we have a sample of size 24, so n equals 24. We're drawing this from a population whose mean is 35 and standard deviation is 1.2. Who thinks the distribution of sample means is normal this time? Who thinks it's not normal? Anyone want to explain?
So the sample size is less than 30 and it's not drawn from a normal.
Yeah, right. So we have two things that can be true for the distribution of sample means to be normal. The first thing that can be true is the sample size is bigger than 30. Well, 24 is not bigger than 30, right? Okay. The second thing that could be true is the population is normal. But the question doesn't say anything about a normal population like example 2 did, right? So there's no mention of a normal population. And since we didn't really mention that there's a normal population, neither one of these two things are true. And the sample means aren't normal in this case, okay? So sample means no, aren't. Okay, and since it's not, you don't have to find the mean or the standard deviation. You're kind of just done. Okay. Any questions on example 3? All right. I think what we'll do is we don't have enough time. Next class, we'll do a little game on finding these values. So make sure you kind of read this up before class on Wednesday. Make sure you're comfortable with finding these values. And I'll see you on Wednesday.